So maybe you don't like the non-parametric statistics, or they're just hard for people to understand or interpret the results. So you want to do something that might make it easier to use normal statistics. And as we go further on in the class, um, normal statistics are particularly helpful for doing linear regression analysis. So how do you make your non-parametric data that may look like this look something more like this, where they're going to do a better job as data points or as clumps of data fitting the normal distribution? So that's the focus here, and it's going to be using the log base 10 transformation. So the log base 10 transformation will not make the data fit the normal distribution all the time. However, it does tend to make it closer to fitting the normal distribution. And in many cases, in fact, it does make the data fit the normal distribution. So it doesn't guarantee that it'll fit the normal distribution. So it's always important or good to check after you do the log 10 transformation to see if it actually worked before you assume your data are normal. And in order to do this, you could do this in Excel by doing a simple calculation and creating a column. And in Stata, we can do it very easily just using the generate command. So we remember before we were generating variables and replacing. It's very simple to do here. So we're going to go back to our practical example where we might have data from our Blue Water Biosciences Kohli plate, data from this Coiler thing, and data from the EPA method. That's kind of the gold standard, the standard method. And we might be interested in seeing whether or not there is a statistically significant difference between the Blue Water Biosciences Kohli plate and the results from like 40 samples with 40 of the paired samples where the water was split. Some was tested for the Kohli plate, and then the same sample was split and tested using the EPA method to see whether or not these are providing statistically similar results. Now, the last time we brought this up was on the last video. We talked about needing to use the different rank, Wilcoxon, matched rank sum and the sign tests and all that. This time we're going to be looking at doing the paired t-test. But in order to do that, we have to figure out if the data are normally distributed and how do we make them fit the normal distribution. So if you remember from the last time, from our practical example, we did the Shapiro-Wilk test for normality, and it showed that all of the data, the Kohli plate samples, the Coiler samples, and the EPA method, they all had p-values that are 0.00001 or less than 0.00001. So very low p-values, obviously statistically different from something. And in the case of the normality test, these are all statistically different from normal. If we were to do the inverse normal plot, doing Q-norm, we can see that here's the normal distribution line, and these obviously do not fit the normal distribution line very well. So that's the Kohli plate, that's the Coiler, it's even worse, and the actual EPA method in terms of whether it fits the normal distribution is even worse. So these data clearly are not normally distributed, a lot because they have a lot of zero or low values with the occasional big spike in data. So how do we straighten these out? So we're going to use this generate command, and we can give it a new variable name. You can call it whatever you want. You can call it Colonel or John, whatever you want. But I like to call it things that make it easier for me to remember. So I'm going to call it generate log Kohli plate. That's my new variable name. So generate the variable log Kohli plate equals log 10 parentheses Kohli plate. This is the original variable. So these are the original data, and we're telling it to generate this variable that does a log 10 transformation of this. And it'll create a new column for us with this new variable name. So when we do that, it'll take something like this Kohli plate of 3, and it does the log 10 transformation, which makes it 0.477. It takes Lake Reba, that Kohli plate value of 1 mpn per 100 mils, and the log 10 of that is 0. 2 has a log 10 of 0.3. 8 has a log 10 of 0.9. So remember, 10 is a log of 1. 100 is a log of 2. 1,000 is log 10. It would be 3 for log 10. So, all right. So if you want to back calculate these on your own, you could go into Excel and hit equals 10 caret sign in parentheses, put in 0.477 for this log, and it'll tell you that 10 to the log base 10 value equals 3. In Stata, you can type in the command display, type in your mathematical equation, and then hit enter, and it'll tell you that our answer is 3. Okay, so we might want to go ahead and do the log transformation for something else, or just so you can see on the practice for these bigger numbers like 3.22. So log, 3.22 log base 10 is actually worth 1,696 E. coli per 100 mils. So remember, 3 log is 1,000, 2 log 10 is 100, 1 log 10 is 10, and so forth. So we're going to transform the remaining data. So we're going to do generate log Coiler for log 10 Coiler, generate log EPA method equals log 10 EPA method, and then it gives us this big table. Or I copied this from Stata, so we can see our new columns that we have here that go down about 40 values, 41 values or so for the 3 different methods. Here's the raw data, and here are the log transform data. So now the question is, did it work? So if you remember earlier, the data clearly were not normal. So now we can do the Shapiro-Wilk test again, just on the log transform data. So what about now? So Shapiro-Wilk, log Kohli plate, log Coiler, log EPA method, and look at this. All the p-values now are above 0.05. Some of them are still maybe below the threshold some folks may use for a normality test, but for you all, we can say that the p-values are greater than 0.05, and we'll presume that the data meet the normal distribution. So big difference from that with those p-values to this. We can also see it visually. So here is the log Kohli plate. Remember it earlier? You can scroll back to the Kohli plate earlier. Look at that. That was the Coiler earlier. That was the EPA method earlier. Now let's look at them. That's the Kohli plate. That's the Coiler. That's the EPA method. They all fit along that normal line a lot better. Not perfect by any means, but they get us to where we can at least use normal statistics. So all are normal according to those p-values. So now the data are normal, we must use the log 10 data. We didn't do anything to the original variables, so we have to use the new variables for our statistical test in order to meet the normal assumption. So now the question is should we do the matched paired rank sum test or paired t-test now to compare Kohli plate versus EPA method? So we did the log transformation, so let's just go ahead, and it worked. So let's do the paired t-test. So when I do the paired t-test, I have to do the t-test on the log transform data. So t-test log Kohli plate equals log EPA method. This is the paired t-test. So you could have done the point and click, or you just type in t-test log Kohli plate equals log EPA method. And when we do that, we get a mean of a log 10 value of 2.01 log, which is about 10. And then we get an EPA value of about 1.93 log, which is not far off of 10. So when we actually look at the mean values for these 41 observations, Stata says the p-value is 0.1884. So since 0.1884 is greater than our alpha value of 0.05, we have insufficient evidence to conclude that there is a statistically significant difference. Therefore, we conclude that the data are not significantly different. So no difference between the log Kohli plate method and the log EPA method according to the paired t-test. So in writing, just so you've got it, the mean value of 2.01 log from the Kohli plate is not significantly different than the mean of the EPA method of 1.93 log, since P of 0.1884 is greater than P of 0.05. Simple enough. Now here's a little warning, just a reminder, log 10 transformations do not always work. So sometimes you do the log 10 transformation and your data are still not normally distributed. And in that case, you're going to have to use non-parametric methods or knowingly go forward violating the normal assumption, at least letting people know that you're knowingly violating those assumptions if you go forward. So that's the basics on the log transforming non-parametric data to fit the normal distribution. So in this case, it actually worked. So that concludes this section on paired test and normal distributions and non-normal distributions. All right, have a good night.